They brought color to the rails and a whole new way of moving America's trains cheaper, faster, and farther. From turbochargers to AC traction. Learn what powers the diesel locomotive on Trains Unlimited. Next. When coal and water stopped filling the locomotive's belly, 150 years of legend and tradition went up the smokestack. Engines that once hissed and puffed now rumbled with a V16 growl. Blaring air horns replaced mournful steam whistles. And the great spectacle of moving parts which propelled steam locomotives was now concealed under a hood. Diesel locomotives share none of the romance and mystique of their steam predecessors. Their legacy lies in their power, efficiency, and reliability. Songwriters don't immortalize diesels, but railroads sing their praises for rescuing them.
The diesel really was a savior for railroads in the 1950s. The diesel enabled railroads to finally standardize in terms of their locomotives in a way they'd never been able to standardize before. All of a sudden, all the things that work in the automobile industry also applied to railroads. Steam locomotives were always handcrafted machines that were customized for each individual company. Now, every railroad company was able to buy locomotives virtually off the shelf, just the way people buy automobiles in a showroom. So by standardizing parts and standardizing technology and procedures, the diesel became a very efficient, cheap to operate tool, and you couldn't deny its power.
A diesel's power comes from the size of its pistons and the number of its cylinders. But its true power comes from how much more it can do than a steam engine, with fewer stops for fuel and water, fewer repairs, and most importantly, fewer workers.
The cost savings brought by the diesel locomotives were mostly unappreciated at the very beginning, but were very rapidly appreciated. Basically, what diesels did is decimate labor. At the end of World War II, there were still almost 1.5 million people working for a steam-dominated railroad system. By 1962, the transition to diesel was almost complete, or virtually complete, and half as many people worked for the railroad. There was less freight, but there were far less employees, and that's what saved the backside of the railroads economically, was being able to lay off all of those people by attrition. Nearly 700,000 people between 1946 and 1962.
The diesel locomotive transformed the way railroads did business. Every aspect of a diesel's operation is more efficient than steam, starting with the way it turns fuel into power.
It's called a diesel when it really should be called, and is technically called, a diesel electric locomotive. Dr. Rudolf Diesel was the man who, before the turn of the century, perfected an internal combustion engine that over time has become the prime mover in diesel locomotives. The first one, believe it or not, used powdered coal. And he'd also experimented with some engines that used ammonia. And the engine was used in ice-making machinery before it was ever used in a locomotive. But that's where the name diesel comes from the man who invented it. Rudolf Diesel won a German patent for his invention in 1892.
His engine compressed a powdered coal and air mixture at great pressure, igniting it without a spark and producing a great deal of power at a low speed of revolution. This type of compact power source was well suited to the size of a railroad locomotive, but the earliest locomotives propelled by internal combustion were actually gasoline-driven. As early as 1892, an 18-horsepower gasoline engine was used to demonstrate self-propelled cars in Chicago. But smoothly transmitting the power from the motor to the rail was a problem. Electric trains overcame this problem in the 1890s. They drew power from overhead wires or third rails and could come to speed smoothly from a dead stop by simply applying more current to the motor. The drawback was that they didn't carry their own power source and required miles of expensive wiring and electrical generating stations to operate. During the first decade of the 20th century, several companies experimented with coupling an internal combustion power plant to an electric transmission. The General Electric Company was the pioneer and most successful. GE started working with gas-electric power in 1906 and sold 5 gas-electric locomotives beginning in 1913. They worked, but they didn't deliver enough power per pound to satisfy the railroads. In 1918, they created 4 locomotives, substituting a more powerful diesel engine for gasoline power. These units, like previous gas units, had their problems too, but GE's venture into dieselization proved to be a big step in the right direction. Motive power evolved on the railroads for many reasons. Meeting early pollution control standards was one of them. Large switching yards with dozens of steam locomotives created great sooty clouds of smoke. Cities like New York started implementing strict smoke restrictions around the turn of the century. Switch engines had to become cleaner burning. By 1925, GE had joined forces with steam railroading's powerful American Locomotive Company and engine manufacturer Ingersoll Rand. Together, they created the first commercially successful diesel-electric locomotive operated by a mainline road. That year, locomotive number 1000 entered switching service on the Central of New Jersey. Its 300-horsepower diesel engine turned a generator which then powered traction motors over the wheels. All modern diesel electrics operate on this basic principle of transferring the prime mover's power to the wheels electrically rather than mechanically.
The industry then started to utilize what we now know today as the diesel engine, but in those days they were referred to as oil engines. The term diesel fuel really didn't become popular until the 1930s.
It was an exciting new technology, but the infant diesel couldn't match the century-old reliability of steam. Early diesels experienced frequent breakdowns. On American railroads, they were relegated to yard service where their performance slowly improved year by year. Along the main line, steam was enjoying its golden age. The 20s represented the decade of steam's greatest innovations. But within 10 years, and after a Great Depression, the upstart diesel would challenge mighty steam for supremacy of the rails. The stock market crash of 1929 and the Great Depression that followed decimated America. It showed in the landscape and, more painfully, on the faces of America's people. The country's industrial base was ravaged. Unemployment reached 35%, and rail traffic dropped by 1/2. Railroads were still recovering from the federal takeover instituted during World War I. Some survived, and some didn't.
Railroads stopped ordering locomotives, stopped ordering cars. There were lots of layoffs. It was just really a bad time for the railroad industry, like it was for everybody else in America.
Railroads needed to jumpstart Depression-era business, and they needed to attract shippers and travelers away from cars and trucks. They stirred a lot of interest with streamlining, combining emerging diesel technology with a revolutionary new look.
By about 1935 or 1936 or so, things began to pick up, particularly with the first practical application on a mass scale of the diesel locomotive. The diesel locomotive kind of kicked into high gear the streamline era, and by the end of the decade we had all sorts of fancy passenger trains just wowing the American public.
In 1934, the Union Pacific led the charge, debuting its sleek M10000. In comparison to conventional trains that pulled heavy steel passenger cars, this streamliner was made of a lightweight aluminum alloy. It was driven by a 600 horsepower petroleum distillate engine and could easily speed its 3 carloads of passengers and 10 tons of baggage over 90 miles an hour. 3 months later at Chicago's Century of Progress Exposition, another streamliner made an even bigger splash with a truly grand entrance. The Burlington route Zephyr raced from Denver to the Exposition, averaging an unheard of 78 miles per hour and topping out at 112 miles per hour. The Zephyr boasted a stainless steel skin and a diesel-electric heart, and unquestionably got the hearts of restless travelers racing.
It was really both aerodynamics and weight that made a difference in the way the streamliner was designed. For one thing, the application of the diesel locomotive meant that you could build a lighter locomotive instead of a giant heavy steam locomotive. So a lighter power plant meant that the whole train weight was lower, you could move at a higher speed. But also the introduction of some new technology in terms of metallurgy and manufacturing processes made it also possible. The trains themselves were lighter.
The propulsion systems for both the M10000 and the Zephyr were conceived by Cleveland, Ohio's Electromotive Corporation. It was founded in 1922 by businessman H.L. Hamilton as an engineering think tank. Electromotive began producing a reliable gas-electric car in 1925, and after becoming a subsidiary of the General Motors Corporation, it began producing diesel switchers in 1935. Its reputation in the field of electromechanical propulsion grew rapidly. By 1941, H.L. Hamilton's little think tank had become the electromotive division of GM and one of the most significant manufacturers in modern railroading. Electromotive built on the success of the M10000 and the Zephyr, powering the Green Diamond Streamliner for the Illinois Central Railroad. All 3 trains were articulated, with their cars and locomotives semi-permanently attached to one another. Alco, the American Locomotive Company, built its own streamliner, the Rebel, for the Gulf, Mobile, and Northern Railroad. Its cars and locomotive could be separated and combined, but Electromotive took the next step in 1937 with a streamlined diesel called the E.
The first real passenger locomotives that could be uncoupled from the train. That is, they could be put on any train and not just on the trains they were built to pull, were 1,800 horsepower per unit. Inside them they had 2 900 horsepower diesel engines, which was essentially the same diesel engine that was in the first switch engines.
Electromotive's E-Series passenger diesels started with the EA and the E1 models, concluding production with the E9s in 1963. The E designation was derived from the 1,800 horsepower, the first model's individual units generated. The engineer sat on the A unit, which led the train. They were often followed by booster or B units, electrically plugged into and controlled by the A unit, increasing the locomotive's size and power. Electromotive's ease, more than any other locomotive, influenced the way diesels would look for the next 2 decades. Over 1,300 units were sold in North America during the E's 36-year production run. One of the rarest and most striking models of the E locomotives was the stainless steel skinned E5. 11 A units and 5 B units were built exclusively for the Burlington route. The lone survivor of the E5s has been restored. It's now the pride of the Illinois Railway Museum, northwest of Chicago. An Electromotive E was part of another milestone event in 1937. That year, the Santa Fe Railroad began the first fully streamlined service of their famous all-Pullman car Super Chief train from Chicago to the coast. It was shiny, it was fast, and it was luxurious. The Super Chief was the latest the railroads had to offer, and frequently drew celebrity passengers. You almost had to be a celebrity to be able to afford the fare of one of these first-class trains. Steam engines started to look a bit old. In 1938, diesel production exceeded steam production, and steam manufacturers weren't smiling.
Advertisements from the various steam locomotive companies in the later 30s were leading the railroad customers to believe that steam really handles the freight. It's okay for these nice, flashy, little lightweight passenger trains to handle people, but when you really have to do a day's work, the steam locomotive is the only way to go, because it's the only thing that'll reliably handle a freight train.
Railroads made their reputation on their passenger service, but made their profit hauling freight. That job, too, was about to be snatched away from steam locomotives, clenched in the teeth of a bulldog-faced diesel. In many ways, 1939 marked the beginning of the end for steam locomotives. Diesels had revolutionized passenger service, but they'd yet to prove their roadworthiness in heavy-duty freight service. That year, Electromotive introduced a freight diesel whose bite would prove worse than its bulldog-faced appearance, the FT-103.
F standing for freight, T standing for 2,700 horsepower. And they put the two sections together and numbered it 103. And they set out in late 1939 to prove to the American railroad system that this locomotive could handle freight. And they toured the United States for 83,000 miles for some 10 months in late 1939, and they showed that it could handle freight trains more efficiently, with less maintenance, less trouble, with less personnel than the steam locomotive.
A popular steam locomotive of the day was the 484 Northern type, which was rated at 5,500 horsepower. The FT was designed to deliver comparable horsepower, 4 units at 1,350 horsepower per unit. By the time the FT-103 began its demonstration tour in late 1939, the United States was already gearing up for World War II. Industrial production was up, export of scrap iron was halted, and rail traffic burgeoned as America's armed forces rebuilt. Japan's bombing of Pearl Harbor confirmed what many felt was inevitable. America was going to war. The threat of enemy submarines loomed off coastal waters. Railroads were called upon to move troops and supplies safely inland. With their personnel and equipment pushed to the limit, the railroad's performance during the war has been called heroic. Many roads could have used efficient new diesels to handle the burden, but war production restrictions limited the number and type of locomotives that could be built. The decisions of the U.S. government's War Production Board would have far-reaching implications for locomotive manufacturers after the war. Namely, which manufacturer would set the industry standards.
The very same diesel engines that General Motors was building for locomotives during the war showed up in many different kinds of landing craft and other small Navy craft. And that production of Navy diesel power shut off railroad diesel production at EMD for quite a number of months.
In 1943, Electromotive had been ordered by the War Production Board to resume building FT freight locomotives, but was prohibited from producing any other type of locomotive. Alco and steam manufacturing volume leader Baldwin Locomotive Works were assigned switcher production. While their switchers were moving boxcars around railroad yards, Electromotive freight diesels were clocking valuable time, hauling trains across the country, and building a favorable reputation.
One railroad in particular got a large fleet of diesels, the Santa Fe Railroad. Santa Fe had a lot of trains operating through desert country, and so the idea of a locomotive that didn't need a lot of water all the time was a nice attraction. But during the course of the war, that fleet of diesels on the Santa Fe and a few others on other railroads built up a fund of experience which showed for all time that these diesels could set records for economy and pulling power and labor savings and all the rest. So at the end of hostilities in the summer of 1945, and the War Production Board limits are now off, railroaders ordered diesels by the droves, and by 1947, 90% of all locomotives ordered were diesels.
Benefiting from their production experience during the war and marketing skills thereafter, Electromotive emerged as the leader in freight and passenger diesels. Alco came in a distant second, manufacturing its flat-nosed FA and PA locomotives beginning in 1946. That same year, Alco began marketing 1,500 horsepower road switchers, locomotives that functioned well in switch yards as well as mainline freight service. By 1949, Electromotive's F-Series freight diesels had evolved from the original FT to the F7s, producing 1,500 horsepower per unit. Railroads liked the sleek bulldog-faced diesels, but some wanted freight units of similar horsepower with better visibility for the engineer that could be used in branch line service. Alco had offered this type of locomotive 3 years earlier in their RS2 model.
So Electromotive developed a constant section underframe, and the car body on top of it was just a sheet metal hood, and that was the very first GP7 locomotive, which had the same horsepower of 1,500 horsepower of the F7. So a railroad could buy the full-width car body Bulldog or the GP7. It had a short hood in the front that you could put a steam generator in it if required for a passenger train, and then a long hood where the engine and generator and cooling system was housed, and good visibility down both sides of the hood.
The general purpose, or GP diesel locomotive, has 2 sets of 2 driving axles. Its bigger sister, the SD, or special duty locomotive, has 2 sets of 3 driving axles. These have remained the 2 predominant styles of diesel locomotives for the last 40 years. Over 2,700 GP7s were built between 1949 and 1953. They were powered by Electromotive's 1,500 horsepower 567B, a 16-cylinder diesel engine. The very first GP7 was purchased by the Chicago and Northwestern Railroad. Today, this locomotive is preserved at the Illinois Railway Museum. In 1944, 91% of locomotives on America's major railroads were steam, and 7% were diesel. 10 years later, it had almost reversed. 79% were diesel and only 19% steam. By 1960, the railroads had completely dieselized.
In one word, the advantage of the diesel over steam, all things considered, was cost. Diesel locomotives themselves probably cost at least as much as large modern steam locomotives, if not more. But you could get a lot more work out of them. They were tireless beasts, really. The steam locomotive might be good for a few hundred miles before it had to be taken off the train and go to a shop for servicing, and by that time it had already stopped for water several times. A diesel locomotive could run from Chicago to the coast without any sort of comparable service except for fuel. As far as its pulling power is concerned, you could add like units to the locomotive until you had the size locomotive you wanted with the same crew, paid them the same wages. Steam locomotive, if the one that you had wasn't big enough, you had to go get another one, and that took a second crew to run it.
Coal-fired steam power had built America. It ran her factories, heated many of her homes, and propelled trains down her rails. But after World War II, coal prices doubled, while diesel fuel remained relatively economical. It became apparent that dieselization was in railroading's best interest. Steam died hard, but it fell to a very worthy opponent. In the pre-diesel era, the big three locomotive manufacturers were the American Locomotive Company, Lima Locomotive Works, and Baldwin Locomotive Works. Alco had built the successful big boys for the Union Pacific. Lima produced the proud and powerful 7,500 horsepower Alleghenies for the Chesapeake and Ohio. And Baldwin simply manufactured more steam locomotives than anyone in America. By the 60s, the big three would disappear like the steam from their vanishing giants. Lima had long been considered the foremost innovator of the three, the scientist of steam, producing some of the most technologically advanced locomotives in the world. Lima didn't even think about offering diesels until it was practically too late. In 1947, it merged with another Ohio manufacturer of diesel engines to form the Lima Hamilton Corporation. Together, they produced 174 diesel units before being absorbed by the Baldwin Company in 1951. Lima, the scientist of steam, had lost the formula and was no more. The Baldwin Company fared only a little better. Its diesel switchers and road switchers were plentiful in the 40s and 50s. But its baby-face cab passenger diesels, as well as its shark-nosed diesels, styled after Pennsylvania's T1 steam locomotives, barely sold 300 units, and those were just their 8 and 12-wheel models.
Baldwin built some locomotives that it called centipedes, with more wheels under them than I know how to count. There's the wheels from one end of them to the other.
The Pennsylvania Railroad owned 24 of the 40 centipedes Baldwin built. They proved to be terrible passenger locomotives and an even greater maintenance nightmare. Baldwin built the last centipede in 1948 and its last diesel 8 years later. Former Philadelphia jeweler and watchmaker Matthias Baldwin had started this landmark company in 1832. It had continually produced locomotives since then and became America's oldest and most successful steam builder. In 1956, after building over 76,000 steam engines and 3,208 diesels, Baldwin Locomotive Works closed its doors for the last time. The most successful of the big three steam builders in the dieselized world proved to be Alco. Alco co-produced the first commercially successful diesel-electric switcher in 1925. It introduced road switchers as early as 1941, but it set out to compete with Electromotive's passenger diesels in 1939 and freight diesels in 1946. Their DL-109 locomotive pulled both freight and passenger trains, but few railroads that owned them were set up to maintain the unusually large pistoned engines Alco chose to power them with.
Well, after it had exhausted that idea, Alco then built the PA. It was a beautifully designed locomotive, particularly in the color scheme of the Santa Fe. It would have helped if they could pull, as well as General Motors locomotives. And in due course, while the Alco PAs were assigned originally to some of the Santa Fe's better passenger trains, they didn't last as long as some of the others.
Electromotive E units outsold Alco's PAs more than 4-to-1, and F-Series freight engines outsold Alco's FAs over 5-to-1.
The major steam locomotive builders tried to build and sell diesel locomotives like they had built and sold steam locomotives, more or less on a custom basis, and they had to build them in their existing steam locomotive factories. While they did produce quite creditable diesel locomotives, General Motors had started brand fresh with the electromotive plant in LaGrange, which was designed solely to produce diesel locomotives. They had a far more efficient plant. They had a sales force that knew that they were selling a different product, and General Motors did take most of the market for quite a while.
Others had an eye on Electromotive's success. Fairbanks Morse had been a railroad industry equipment supplier since 1830. In 1944, it started building diesel road switches, and in 1949, it began competing in the full-size locomotive market. These units, like their switchers, were powered by the company's patented opposed piston engines. They were developed under contract with the Navy and literally had pistons upside down firing in sync against the ones below them. The powerful OP engines were successful in marine applications, but proved too difficult to repair and maintain in the harsh railroad work environment. In 1963, after building 1,460 locomotives, Fairbanks Morse left the market. One other manufacturer entered the freight and passenger locomotive manufacturing business late. Defying the odds, it's become a formidable competitor to Electromotive. It built the first practical gas-electric switchers, teamed up with Alco to build the first successful diesel switchers, and has supplied other locomotive manufacturers with electrical components for their engines. But more people today know them for their light bulbs and TVs.
It didn't take General Electric very long in the middle 50s to realize, say, why aren't we in this business? Why are we selling electrical components to Alco, Baldwin, or Lima? So by the late 1950s, General Electric started to produce a locomotive to compete with General Motors, Electromotive Division, the U-25 series locomotive. Now, because they built their own electrical system, now they're competing with General Motors and Alco. As they improve their electrical system, why would they sell their improved electrical system to Alco? That's another competitor in their mind. So Alco always got the secondary line part, and pretty soon Alco went out of business and declared bankruptcy also. General Electric became stiffer and stiffer competition, and that is the American way.
Successful locomotive building has always relied on a certain amount of experimentation to breed innovation. Some railroad experiments have been more successful than others.
The German Krauss-Maffei company in the early 1960s developed a diesel hydraulic with a fluid clutch system to try to compete with the electric transmission system of a diesel-electric locomotive. They in turn required huge amounts of maintenance. The European diesel engine was not successful in the United States because they weren't designed for heavy haul operation, and they required a lot of maintenance and attention.
In 1956, Electromotive produced a pair of lightweight trains based on GM's standard intercity bus body, The futuristic styling of the locomotives pulling them curiously resembled GM's automobiles of the time. Even electromotives struck out now and again. The Aero train didn't catch on and now resides in a rail museum. General Electric had moderate success with several models of gas turbine units it built for the Union Pacific, locomotives that were powered by jet engines.
The idea was to produce tremendous amounts of horsepower out of one locomotive, and to do it on essentially residual fuel oil, something that's pretty cheap. We had them all the way up to 10,000 horsepower, and that's a lot of horsepower in one locomotive. One of the big problems with them was the noise. They made as much noise as a 747 at takeoff. So there were cities you couldn't take them into without being arrested. We ran one into Los Angeles once and never did that again. They were pretty good across the desert because you didn't have to worry about the noise, and they would pull more than steam locomotives, but you didn't have to put water in them or anything like that. They just had an insatiable appetite for fuel. By the mid-70s, fuel prices kept going up, and that's what eventually put them out of business.
During nearly 20 years of service on the Union Pacific, the gas turbine size and the noise they made weren't the only things that drew attention to them.
The turbine had an exhaust stack that was about 8 feet in diameter, and the exhaust temperature coming out of a turbine was something like 12 or 1300 degrees. There's a story about stopping one over at Laramie with the exhaust underneath a concrete bridge that had a blacktop roadway over the top of it, and that it melted the blacktop. Most of it came down through into the stack of the turbine, which spit it right back out. But they had to take the road out of service because there was a tremendous pothole right in the middle of that bridge.
In 1969, Union Pacific combined its passion for high-powered engines with its celebration of the 100th anniversary of the Transcontinental Railroad, which they helped create. The UP commissioned Electromotive to build the last of a series of double diesels. The DDA-40X Centennial locomotive was essentially 2 diesel locomotives built on the same frame. 47 were built, only 1 remains active today. It's part of Union Pacific's public relations program. At 98.5 feet long and 6,600 horsepower, the DDA-40X is still the longest and most powerful diesel-electric locomotive in the world. It's a fitting tribute to the only major railroad in America that has never changed its name since pulling its first train.
The real drive in railroading, in many ways, first of all, is to make money, but also to be as efficient as possible in doing it. And the great drive over the whole course of railroad history is the drive for more horsepower. In the development of locomotives, the idea was always to build a locomotive that could more effectively and more powerfully haul more stuff a greater distance. And that hasn't really stopped with the diesel. The whole idea is to build more and more power into fewer and fewer diesel units so that you can do more and more work with fewer people.
Manufacturers have utilized various technologies to maximize the power of their diesel locomotives. Over time, the most practical methods have often proven most effective. Just like the automobile, increasing the size of the locomotive's pistons or the number of cylinders in its engine has boosted power. The first successful diesel electrics had 6 cylinders. Today, 16 to 20-cylinder engines are common. Cylinder dimensions are another factor.
Nowadays, automobiles are into liters, but the standard Chevrolet 350 V8, that means it's 350 cubic inch displacement for the whole engine. The 567 diesel locomotive developed by General Motors was 567 cubic inches per cylinder. And you had 16 cylinders that operated at 800 RPM and produced 1,350 horsepower for the FT locomotive.
The space on a locomotive frame is limited. Again, as with the automobile, a solution to increasing horsepower without significantly increasing engine size has been turbocharging. By forcing more air into the cylinder with the turbocharger, the explosive force of the igniting fuel increases, raising the engine's potential power. Manufacturers like General Electric routinely turbocharged their engines, but Electromotive didn't offer their first factory turbocharged units until 1958. Turbocharging increased the output of GM's 16-cylinder engine from 1,800 to 2,400 horsepower. Perhaps the greatest breakthrough in modern locomotive design was the introduction of AC traction in 1989. A diesel's electric traction motors have traditionally run on direct current, or DC, the same type of current in flashlight and car batteries, only much stronger. Alternating current, or AC, is what powers homes, businesses, and industries. It's more efficient and can produce greater output from smaller motors. AC alternators, which create the electricity, are also smaller than DC generators of the same capacity, and the AC traction motors they power won't burn out at super low speeds like traditional DC motors can. But they allow the locomotive to pull heavier trains up steeper grades unassisted and are cheaper to maintain. AC propulsion isn't as easy to control as DC, and only became feasible with the advent of microcomputers which regulate the process.
The new locomotives, which are the SD90 Max that we get from EMD and the AC6000s that we get from GE, the horsepower itself, of course, is just a little bit below what we had in our Centennials at 6,600. The big difference in these is that with the AC traction motors and the microprocessor controls, there is a tremendous increase in adhesion and a tremendous increase in tractive effort. And what that does is it allows one 6,000 horsepower AC locomotive to replace 2 or 3 3,000 horsepower DC locomotives. So it's quite an innovation. The potential of these things is awesome. And we think it won't be too long before you'll be seeing 10,000 horsepower locomotives, 12,000 horsepower locomotives. It's just amazing.
The first diesel-electric switchers were developed in part to comply with pollution controls in big cities. In smog-challenged Southern California, the Los Angeles Junction Railway Company is experimenting with another emerging technology. Liquefied natural gas locomotives are very similar to diesel electrics, only they produce virtually no emissions.
There's 4 locomotives. They're prototypes. They were put in service in 1994. There's 2 on the Union Pacific Railroad and 2 on the LA Junction Railway. Being gas instead of diesel, it has a different firing mechanism. It actually uses spark plugs, essentially like your automobile does. And it has different fuel tanks, which are a thermos bottle fuel tank. The advantage to these locomotives over the diesel switcher locomotives is these are cleaner, they're quieter, there's less maintenance to do on them. It makes more sense environmentally. The tonnage they'll pull, their wheel slip system has better control, so you can pull more freight with less locomotive.
At the present time, liquefied natural gas is costlier to use in rail applications than diesel fuel, something that will likely change as the technology develops and gains wider acceptance. But in an environmentally and politically sensitive world, cost can no longer be measured in dollars alone. In many ways, the development of the diesel locomotive paralleled the post-World War II transformation of American society. As the country and the needs of its population grew, mom and pop stores were replaced by supermarts and national chains. Uniform tract housing began to edge out uniquely individual neighborhood homes. In the modern world, faster and cheaper became better. On the rails, handmade steam locomotives were displaced by standardized, mass-produced, and mass-marketed diesels. Some of them were faster, all of them were cheaper to run, and ultimately they were better for the country's changing transportation needs. Many people lament the passing of steam, but without the cost savings allowed by diesels, the railroads themselves might have become extinct. Eventually, another technology may replace diesels just as diesels replaced steam. It may come in the form of electrification of all mainline railroads, with propulsion power coming from overhead wires generated hundreds of miles away, or perhaps from a power source that's not yet been invented. By that time, trains might not ride on rails at all.